It's the last talk for today. An introduction to and a survey of TLS security. Sounds scary. Aaron Tauner.
Hi. So I'm going to present on TLS security today. There have already been a couple of talks on the topic, which is why I'm going to skip a couple of the slides. I'm going to put up the slides right after the talk. How many of you guys have been to the mobile SSL failures talk, the Bleichenbacher talk, or any of the other talks? Okay, perfect. I won't explain Bleichenbacher or how an RSA key Diffie-Hellman key exchange works or RSA, because that's like 20 minutes and I have 91 slides, which is far too much. So an overview. I'm going to talk shortly about information security and cryptography. Going to skip the parts I just mentioned. I'm going to explain a bit how TLS works. Most of the speakers already did that had previous talks. I'm going to talk a bit about TLS extensions. There are so many, I can't fit them into a talk, but a bit. And then about history and attacks, which is the largest part. And I merged a part of a workshop we did, TechElu, into the talk, which is on ITF efforts with regard to like the post-Snowden area. Post-Snowden events and everything. We see TLS on a daily basis, of course. Everybody uses it for banking, blah, blah, blah. We all know it. This is an actual survey of the Alexa top 1 million taken on November the 5th of this month. About 23% of the websites on the internet are currently secure in terms of good cryptographic security. These are cipher strength. And 500 of them are still vulnerable to heartbleed, so you can read remote memory, of course. Only half of them support forward secrecy, and only about, 38% support strong forward secrecy. Most of them are still vulnerable to the Beast attack, which has been presented 2 years ago. And that's not a talk about cryptography, so I can't go into too much detail. By the way, are the slides readable? I can just inverse the whole screen and then it's white on black, black on white. Okay. So for us, information security manages 3 things, among other stuff, but it's basically the CIA thread. It's really quoted. It's confidentiality, integrity, and availability and authenticity. Which is what most security protocols try to achieve. Confidentiality, of course, tries to mitigate that an attacker can read your clear text and the data you're going to send between 2 parties in a protocol between 2 people or 2 machines that are trying to interact. An example of that is the IS encryption standard. We talk of encryption and decryption. There are different block cipher modes which are used because block cipher only works on blocks and not on a stream, like as in a protocol. There's Cbc Mode, counter mode, Galois counter mode, which is the preferred mode today in TLS standards, and the only secure mode. It's not secure on mobile phones, by the way, which is another problem. Cbc Mode, this is how Cbc Mode basically works. It's from Wikipedia. You have like you're basically updating the ciphertext with an initialization vector and a nonce. The same thing works for counter mode, where I do that in parallel. So that's inherently parallel because you have a nonce and you can update the counter without having packets in consecutive order. Integrity assures the consistency of data, so that data cannot be tampered with, or that you cannot, for example, break a protocol by just injecting false data, and then the other side basically gets fast by packets that aren't valid at all. This would be, for example, and MAC would be used, for example, SHA-265, SHA-1, or in the case of authenticated encryption with associated data, it's Galois counter mode and CCM or OCB, which aren't really standardized because they have patent issues. And examples about authenticity and non-repudiation are RSA, DSA, ECDSA. These are basically used for certificates. All of you know that. Most of you have probably used a web server and set one up, so that's nothing new. A new algorithm would be ED 25519, which is by Daniel Bernstein, Tanja Lange, and 5 other people, which is going to be standardized soon. I'm going to come back to that. This is how RSA works. I'm not going to go into that, even though it looks really cool with LaTeX beamer slides, but no. So there was a guy doing a presentation on Bleichenbach attacks. This is why I'm also not going to go into that, because this is basically a thing you can talk about half an hour for that. And Kee Exchange Algorithm, Diffie-Hellman was also explained in other talks. So I'm also going to skip that. It's like Alice sends stuff to Bob, Bob sends stuff to Alice, they have a shared secret, and then you have a pre-master key. And for forward secrecy, what you basically do is you have a Diffie-Hellman exchange where Alice and Bob basically discard their public key afterwards. So in SSL terminology, you have cipher suites, which are standardized, and there are like 150 of them. Most of them are insecure. An example would be using elliptic curve Diffie-Hellman, which is used for, which is an ephemeral, in this case ephemeral, so it provides forward secrecy, RSA for certificates, AES for confidentiality, and Galois counter mode and SHA-265 for the certificates. This would be the standardized parameter that is standardized by Jana. They look quite different in different implementations. Because, for example, Openssl, back when they started implementing TLS, back then SSL version 3, there weren't any standardized parameters to use and to begin with. So they came up with their own scheme, and later they didn't use the Jana schemes. The only people that actually use the correct Jana schemes are Apple, actually. And Microsoft also uses them, but they add the curve that is used for the elliptic curve and ECDSA stuff. Yeah, I'm going to point out how TLS works a bit. So you have a TLS record that is basically one byte of the type, which says which TLS type is going to be transmitted, the TLS version, and the length of the packet, and then the message. Most of these types look the same. There are different TLS types like alert, or as you have heard, the heartbeat type. I've always to be careful not to call it heartbleed, which happens all the time. Then there are different types for handshakes and messages, which have already been discussed in the other talks. So the client says, hello, I'm here. Server says, hello, here, have my certificate. And the server key exchange and a certificate request. And then the server hello is done. The client says, yeah, perfect. And we're done. And in the case of a client sending a certificate, you have a client key exchange as well. And then they both agree on a common cipher suite, and you can send application data. And there are some esoteric things like session resumption and false start, which have both been implemented and standardized in IETF for the reason of better performance in large web environments. Session resumption basically resumes a previous TLS session you have had with a client, or a server with a client, or two machines with each other, and false start isn't used anymore because it's completely insecure, basically. Google came up with that, and they basically send it to hell shortly afterwards. Then there is online certificate status protocol, which you might have also heard about. It's basically an online protocol. Back in the day, we used to have certificate revocation lists, which most browsers still are able to use. If you use Chrome, there is a binary diff, a patch that is sent in the background of certificates that are valid or invalid, or basically CAs that are valid or invalid. Another possibility is to use online certificate status protocol. It's inherently broken. You can man in the middle the protocol. So basically, you can just say, oh, there's another certificate authority, and it's all correct. So you need to use OCSP stapling, which basically prevents that. But OCSP has such a high latency that it can't be used in reality. Usual latency requests for OCSP are between 200 and 400 milliseconds, which in the case of like websites that need to be loaded and have a good user experience and UI is just too much. And with Heartbleed, where a lot of certificates were revoked, basically the whole OCSP system worldwide broke down. So that's not really a good solution. And I'll come to a new solution that has been proposed a couple of days ago at the end of the talk. Then there's Hsts, which is now standard, which basically says that once you have a TLS connection set up to a server, the server says, hey, for the next, say, 2 or 3 months, please only do HTTPS connections and never fall back to HTTP. And there's security renegotiation, which I'm also going to talk about a bit later. Google also drafted Speedy, which some might use. There's like a guy from Akamai somewhere around here. Maybe he left the room. He already knows this stuff. And yeah, you have the whole issue with X509 and the Web of Trust, which certificate transparency approaches by Google is trying to solve somehow. You basically have a public log of all certificates that have been issued and all certificates that are used or are in use. So you can easily see if somebody is issuing a certificate that is not correct, like a malicious certificate or a malicious certificate authority. So that was the background on TLS. Very fast, I'm sorry, but it has been discussed already a couple of times. So Ssl was first standardized with version 1, was engineered as a project within Netscape and never got public deployment. It was completely broken, of course. They tested it internally. What they published as an IETF draft was Ssl version 2, and which it got later implemented in Netscape and in other libraries. And that was, of course, also completely broken and should not be used. Shortly afterwards, Ssl version 3 was designed by a couple of other people from IETF that came up with some of the attacks, which was also broken. And back then, on a side note, you had the whole issue of export ciphers in the United States. I'm not sure if you guys are familiar with that. Basically, there was a restriction of software where if you have a cipher that is above 40 or 50 bits, I think 40 bits, you couldn't export it from the United States in software, which is why they printed T-shirts. EFF, I think, printed T-shirts with a Perl script implementing RC4, which is nowadays, of course, broken, but still. The Ssl version 3 protocol was susceptible to fallback to version 2, which means, of course, you can do a man-in-the-middle attack. The protocol leaks a known plaintext, which means you can do cryptanalysis on it and basically recover plaintext. You can do replay attacks on anonymous Diffie-Hellman. Anonymous Diffie-Hellman is basically Diffie-Hellman without certificate, which you shouldn't use anyhow, but some people use them for machine-to-machine communication. Then TLS version 1 was standardized. That was in 1999. Some issues of Ssl version 3 were fixed. There were new ciphers introduced, like triple DAS, DSS. And a couple of years later, in 2002, Vodeno, I'm not sure how to pronounce his name, came up with the Cbc padding attacks, which are like Poodle is also one of these attacks, which is still an issue for all Cbc modes, which I've talked about earlier, like doing a stream cipher, basically doing a stream of block ciphers. A bit later, there were TLS extensions standardized, not a new version of TLS actually, but just extensions like extended handshake, client hello, server hello, server name indication. You use server name indication nowadays for virtual hosting. For example, you don't want a TLS IP address to just serve one host. You want multiple hosts, as most of you know, for example, Apache or Nginx or any other web server. SNI allows this. It actually leaks metadata, of course, because everybody that is reading the connection data can see which host a certain client is trying to connect to. Yeah, and OCSP was standardized as well. Then was the first remote timing attack on RSA, which was an Openssl timing attack by Boneh and Brumley. Basically, you send a specially crafted client key exchange message, measure the time between the client key exchange message and the alert Openssl sends you, do a bit of statistics, and retrieve the private key. That's, of course, an oversimplification. I have like the papers all linked there. The next attack was also by Bordenau, which I explained earlier. It was a successful intercept of IMAP, TLS channels, and passwords. It's an interesting paper. I didn't know about the paper until half a year ago when I first researched the talk I did, which is also the same talk I do here, but a bit more extended. Then it was a chosen plaintext attack by Bart, which actually prompted that TLS 1.1 got standardized. Then there was, TLS 1.1 was standardized. The expert ciphers that I mentioned earlier were removed. Session resumption was added, protection against these CBC attacks. And the IANA parameters were standardized, which was in 2006, of course. Openssl, which was originally called Ssl Lay, was active since I think 1996 was the first release of it or something like that, for example, and other implementations as well. Shortly afterwards, 2 years later, there was TLS 1.2 protocol was standardized, which basically added better pseudorandom functions and authenticated encryption with associated data, Galois counter mode, CCM mode, and RES cipher suite, like the extended cipher suites. Now for some cool attacks. There was an attack by Stevens, Applebaum, Landstra, and a couple of other people where they basically did a hash collision of a certificate authority root certificate and could do an active man-in-the-middle attack. This was a 25C3, which is a really awesome talk. Just watch it. It's a nice presentation. The next attack was by Maximilian Spike at Black Hat in 2009. It is the Ssl Sleep Attack, which caused HSTS to be standardized. Basically, an attacker client connects to server, an attacker intercepts the connections the connection with man-in-the-middle, sends an HTTP 301 move permanently. This is, of course, for HTTP connections, and fakes basically an HTTPS connection and can read the plain text afterwards. And then there was another cool attack by Moxie where he used the null terminating of strings when issuing certificate requests for large CAs. So for example, you had www.paypal.com null terminated with thoughtcrime.org, which is his personal domain. That would be valid for paypal.com. But the certificate authority was originally thinking that it was a request for thoughtcrime.org. All CAs, of course, fixed it almost immediately, but it's a curiosity because these people are basically snake oil, right? They sell security and don't even have implementations that check input validation, which is the most basic thing, and this was in 2009. It's not long ago, right? So IETF published a standard in 2011 forbidding basically SSL version 2 and downgrading to SSL version 2 in all TLS-enabled connections. In 2011 also there was the Komodo breach, where basically an attacker issued 9 certificates for via a reseller account for Google, different subdomains of Google, Google Search, Google Maps, Yahoo, Live.com, Skype, and so forth. Komodo issued a statement saying, yeah, that's a 1 in a million case. It won't happen again. Shortly thereafter it did. Then there was the Beast attack, which Dang and Risso, sorry, I'm really tired, demoed at Echo Party live on the PayPal website. Basically, a phishing victim visits a certain website. A script makes a genuine request via JavaScript. The attacker records the encrypted session information and then then tries to guess the session cookie, and this is also again a CBC attack. Yeah. Shortly afterwards, there was the TrustWave CA incident where it turned out that TrustWave, a big certificate authority, sold DPI certificates, basically certificates that are wildcard for every big domain, to big corporations, banks, and large government institutions so that they could spy on all of their employees. They issued a statement saying we only do that for really good customers, but still. Then there was the DigiNotar breach. A couple of hackers got into DigiNotar, issued again a couple of certificates for big name companies and domains like Google and stuff like that. DigiNotar acknowledged the breach. Shortly afterwards, they filed for bankruptcy. I talked to the Fox IT guys that actually did the forensic analysis of DigiNotar. It was really interesting. Can't go into detail, but they never got paid for the investigation, neither by DigiNotar nor by the. So it's a company from the Netherlands, so neither by like the Netherlands government or something like that. And then there was another attack in 2012, which is a scientific paper basically, doing a certificate validation fuzzing on all of the standard implementations as well as language libraries, and found, of course, problems with all of the common SSL and TLS libraries, especially open source libraries, which they were auditing, as well as EC2, AWS, PayPal SDKs, curl, PHP and Python stuff, and Java middleware. There was a list of I think 20 or 30 different Java middlewares that were susceptible to this attack. Then was another attack by Dang and Risso, the crime attack, which is basically based on TLS compression. An attacker sees the length of the compressed ciphertext, and the compression has direct effects. So if you can influence what a website displays or what is transferred via the encrypted channel, and you see different lengths to do the compression, then you can basically retrieve parts of the data, for example, cookie information. Based on an earlier attack, there was, also an attack by Dang and Rizzo, there was an attack on HTTP requests, HTTP, yeah, it was a timing attack that extended on the crime attack I talked about before. And then recently there was in 2013 an attack on Cbc Mode, which basically makes Cbc Mode completely insecure. And it's an academic attack, and it's extremely latency sensitive, so it only works on a local network, but it only will take a couple of years until another attacker finds a better solution for the attack. And this is why none of the big web providers do any Cbc Mode anymore. And when this attack initially came out, most of the web companies and most of the security engineers said, yeah, switch to RC4, it will work far better. Shortly afterwards, RC4 cipher turned out to be broken. So we only have AES in Galois counter mode left, which only works in TLS 1.2, which a lot of clients don't support. For example, you can't support Windows XP at all, which basically leaves out all of Asia. For example, there is a 90% deployment rate, I think, in China or something like that, or 80%. Peppy has numbers, I don't know. Was it you? I don't know. Okay. Huh? Still way too many. Yeah, still way too many. It's the same for India. So this is an issue nobody really knows how to deal with, but yeah. After these Snowden revelations, there was this discussion on the elliptic curve random number generator, and Daniel Bernstein and Tanja Lange had some issues with some of the NIST standardized curves that were in use back then and standardized by IETF. These are the curves used for elliptic curve Diffie-Hellman and elliptic curve digital signature standard. They have put up a nice project detailing some of the attacks. I mean, you really have to be a mathematician to understand those, or talk to these people so they can give you a dummy version of these things. And they actually did. There's a nice talk from ShmooCon last year where they basically explained this for non-cryptographers. Then there was another attack based on crime. which is very similar to crime, but uses HTTP compression instead of TLS compression. It's basically the same attack, but with HTTP compression instead of TLS compression. Yeah, and this year there was a nice paper, you won't be needing this anymore, from a German university on removing unused certificates in trust stores. They compared 38 million HTTP certificates that were in use by websites and browsers, and it turned out that 140 certificates in the trust stores in major operating systems were completely unused. Of the 426 or something certificates, only 66% were even in use. So most of the certificates you have in your browser or in your operating system trust store, in your Java trust store, are unused and could probably be used by an attacker. These are really small certificate authorities, maybe 2-person companies. I know of one in Austria, for example. And these are still in your browser, and most of these have been like since 1995, 1996, something like that. It's really hard to get into a browser or in an operating system trust store these days, but back then it was rather easy. Then there was another attack at last IETF. There was an attack on a triple handshake attack. Basically, that only works if there's a thing that is called client certificates for TLS, which I mentioned before, that is used if a client needs also to be authenticated. For example, has any of you used Puppet or Chef or any of these automation tools? Maybe some of you have tried them, or any other, like for Windows deployment tools, it's also in use. Then a client also has a certificate and says, yeah, I'm a valid client, because for a web server, of course, you don't really care if a client is valid or not. Everybody can visit your website, but if you only want to send data to a specific client, then you need a client certificate as well in TLS. And there you have basically a triple-way handshake where a man-in-the-middle attacker man-in-the-middle both the connection from the server and from the client, and establish a secret which he knows and can basically decrypt the whole traffic. Then there was another attack called the Frankencerts. It's a GitHub project, actually. They basically did fuzzing of all X509 related code in all popular implementations. It's a really good project, and it can be used by everyone. It basically just demos that the code that is used to validate certificates and generate new certificates is really bad. This is mostly due to ESN1 being used for standardization and X509 being a complete bullshit and overblown standard that is, I mean, it has been in use for years now, but it's really bad. And there is no real alternative right now. And then, of course, you all heard of it. There was the heartbeat bug, where you send the heartbeat extension and get some remote memory. And I wrote an ML plugin if anyone wants to use that, because the ML plugin that is in the official repository is bullshit. It's really bad. Then there was another attack at Black Hat. There was an attack presented where an attacker uses SSL version 3 downgrade. Fuck, only 10 minutes left. When an attacker uses SSL version 3 downgrade, and with SSL version 3 you have, in larger web environments, you share session caches between servers. And for example, you could do a request with where man-in-the-middle attacker does a downgrade to SSL version 3, and then session caches are shared among multiple front-end servers. And you could do a request for www.company.com and then do another request with git.company.com, which might be an internal repository, and it would still be valid because it was coming out of the cache, like the authentication for it would come out of the cache. And that still works today, actually. It can't really be fixed because all of the large web environments use SSL caches, and it's an implementation and a protocol issue. And then there was the Poodle attack, which most of you have heard of. It was only a couple of weeks ago. Again, a man-in-the-middle attacker downgrades to SSL version 3. The attacker does block duplication and gets on average on 265 requests 1 byte, which is extremely much. There is actually an extension that has been proposed prior to the Poodle attack, which would prevent the downgrade to SSL version 3. It's not standardized, and there's a lot of discussion in IETF. And on the last patch Tuesday, there was the remote code execution in S-channel, in Microsoft S-channel, which enables a malicious attacker with a client certificate, even if it's not supported, to send a payload in the signature, in the elliptic curve signature. There's a nice write-up of it, and I've tried it out before the talk. It takes you something like half an hour to actually do that. Yeah, and then there were a couple of other implementation bugs. I didn't even discuss all of them. Only this year, in 2014, there were 24 security advisories for Openssl. There was the Apple GoTo fail. There was the GNU TLS fail. A couple of other GNU TLS vulnerabilities and wrong use of Crypt API all over the place in different implementations of server, client, software, and middleware. And yeah, for this crowd, it's up to you to find more bugs. So I'm going to talk a bit about IETF. I hope it's still possible, but I'll just really speed up. IETF basically works this. You have the Internet Society that governs the Internet Architecture Board. The Internet Architecture Board says what the IETF and IRTF should be doing. IETF is the Internet Engineering Task Force, and IRTF is the Internet Research Task Force. So every time Internet Engineering Task Force doesn't know what to do, they ask IRTF. In these, they have steering committee, and then there's different working groups. For example, HTTP working group, TLS working group, FTP working group. No, there's no FTP working group, but there used to be. And I'm only mentioning the IRTF because I'm going to talk about the Cryptography Forum Research Group, which is a research group of only cryptographers that basically consult the TLS working group, IPsec, and a couple of other security-related standards on what curves should they use, what ciphers they should use, and so forth. And all of the researchers that published security papers I was referring to earlier are now in the Cryptography Forum Research Group, so that's really a good move. So after the Snowden leaks began, there was a new mailing list created within the IETF. All of the internet engineers were pissed as well, as were hackers, of course. And these people started to work on encrypting the internet. At IETF 89, I was invited there with Aaron from the Better Crypto project. There was a strengthening against the internet against pervasive monitoring workshop. A lot of good feedback and ideas for TLS and encryption in general for the internet. The main takeaways were we need a solid threat model. What should we defend against for the TLS working group and for other working groups, for example, IPsec and everybody that's doing something with the cryptography. And these people needed solid guidance on which ciphers and which curves to use, because most of the people that are actually writing standards are engineers and programmers and not cryptographers. Some of them are, but most of them are not. Then there were other working groups created due to the Snowden leaks. For example, the UTR working group, which I'm involved with. It's a working group on utilizing TLS in applications, basically saying which kind of ciphers to use, how TLS should be used, which API calls should be used, and so forth. The TLS working group is updating the protocol with TLS 1.3. It's not a standard yet, but it will be in half a year or so. New ciphers are being added. One is Charger 20, Poly 1305, which is a very fast authenticated stream cipher, but in this case it's used as a block cipher for mobile devices in this case, because the Gallowa counter mode I talked about before with IIS, this has timing attack problems on mobile platforms, at least on some mobile processors. And that's why Google basically tried to standardize this. There was another working group which didn't get much feedback, but they're working on TCP encryption. It's called TCP Inc. TCP Inc. with security. It's based on a paper by Bonnet, one of the researchers I talked about before. It's basically opportunistic encryption on the TCP level. So every TCP connection would be TLS encrypted. Without using TLS, it's on the TCP level. Deprive is a really, it's two or 3 weeks old. It's a new working group on DNS privacy. And the Internet Architecture Board put out a threat model. There's a draft by Bruce Schneier and other people. And there's a new working group on public notary transparency, which is basically doing a standard for certificate transparency, the idea by Google to use these logs and stuff. And yeah, the Cryptography Forum Research Group was tasked with coming up with new curves and with curves that are trusted really fast and could be implemented in software and in hardware really good. So one of these proposals is curve 255.19 from Dan Bernstein, the nums curves from Microsoft, and ED 448 Goli logs from Mike Hamburg, which is a funny name. I always like it. So there is no real consensus, but until the end of the year, the CFRG should have consensus on which curves to use, and these are going to be implemented in not only TLS, but probably also IPsec if there are updates to the protocol. And yeah, certificate transparency is now being worked with as an IETF standard. There's discussion on mandatory encryption for HTTP2. This is actually a proposal by Google, by Adam Langley. It has some bad feedback in the working group, but it's mostly it's still discussed. I don't know. And the Internet Architecture Board put out a statement 2 or 3 days ago that every new protocol that should be designed for the within the IETF should be encrypted by default. The Internet Society commented that statement, which is really awesome, and I think that's really important. So even for like management protocol stuff that usually, where it usually doesn't matter if it's encrypted or not, you should have encryption by default, just in case somebody really puts it on the internet. I mean, there is enough IPMI. In Austria, there's like 4,000 IPMI. There's 4,000 IPMI machines on the internet, and this is a protocol that has encryption, but the encryption is bullshit. You can basically say it null cipher, and then you're root, at least on the IPMI. And mitigation is basically pretty easy. Use the most current software, listen to experts, check out our paper at bettercrypto.org, which is especially focused on management people and system administrators. It tries to explain some of the crypto, but doesn't go into too much detail. There are a lot of cool tools to test for TLS bugs and TLS vulnerabilities in the appendix of the paper, which you should really check out if you're a pen tester and a security researcher. It's like all of the tools we could come up with in half a year in the appendix of the paper. And yeah, keep track of standards evolvement and TLS security in general. And that's a double slide, basically. But yeah, they're working on TLS 1.3. The SSV stuff is for the Poodle attack, which we talked about. And cryptographic libraries seem to be far more audited since the Snowden revelations. Everybody's looking at Openssl, GNU TLS code, Apple Crypto Framework, and so forth. Then there are new ideas for trust on the internet that is not based on certificate authorities. One of them is still using certificate authorities, but distributing the trust for these authorities and monitoring it via logs and basically comparing the logs and seeing if there is misissuance. HPKP is a new header that has been standardized 2 weeks ago. It's an HTTP header where you use public key pins. Basically, you pin the public and the private key of a server. 5 minutes left, huh? A lot of time. Is it with questions or without questions? Fuck it, I want to drink beer. They have no alcohol here. Another cool project is Let's Encrypt. It has been announced 2 or 3 days ago by the EFF, Cisco, Akamai, University of Michigan. These are the guys that are doing SetMap. They're also involved with it. It's basically a system to have a free certificate authority for everybody without paying for the certificates. They design an online protocol that every server can just request a new certificate, get it, and it's going to be monitored via certificate transparency. And HPKP I already talked about. And yeah, trust the mouth is like a quote from Schneier. Implementations are still a big issue. So if you're a security researcher, look at GNU TLS code, look at Openssl code, look at S-channel code. You can't look at it, but you can fuzz it. Software bugs are a big issue. Most of the bugs that we saw this year are software issues combined with protocol issues like SSL version 3 and protocol design. I mean, this is now taking almost 20 years, and we are now coming to a protocol with TLS 1.3 that is somehow secure. So that's a takeaway. Yeah, thanks for your patience, and sorry for me being so chaotic, but I'm not a good speaker. So are there any questions? No.
There must be questions on TLS.
TLS guy is asking something.
Hi, yeah, thanks very much for the presentation.
Yeah.
One remark regarding the issue of using current software versions.
Yeah.
The special example of Android, because I happen to know a little bit about it.
Yeah.
Use Android 5.0 because all the previous versions of Android are using RC4 by default.
Yeah, they are.
And another remark using the Let's Encrypt proposal. It's really, really great, but it doesn't protect you from the root CA misuse, so watch out.
No, it does protect you from the CA misuse in terms of they mandate a certificate transparency. So you basically, I mean, you know certificate transparency, I guess,
yeah.
right? So certificate transparency is mandated. What the fuck? Certificate transparency is mandated in the whole design of the protocol. You can check it out. It's on GitHub, the design spec. It's not a final design, but basically every Let's Encrypt certificate authority would have also to be a certificate transparency log and share it with every other log and with other public logs. So, and it's a really good design, but it only protects you against passive attackers, basically. Yeah. Better than nothing, and it's free.
And there's a lot of passive attackers lurking on the interwebs, which helps to get them out. More questions? We still have time. Yeah.
By the way, it's the first security conference I've been to where there's no Club Mate or beer, which would have helped. No Club Mate nor beer. It's okay.
I wonder if you are working in these TLS working groups, whether you can shed some light on the process, because sometimes we had some internal discussions also, and if there are some protocol related issues being detected, some flaws. I mean, there is the delicate choice of amending or correcting older versions like TLS 1.0, or correcting it with a newer version.
You can
correcting it only with a newer version always gets you into an interoperability issue. So what is the process in these working groups to decide to do either or?
So first of all, most of the security issues that were discovered in the last years were actually discovered by people within the IETF working groups. Not all of them, but mostly. So that's one point. You can't basically update an old protocol. It's going to break a lot of stuff. It's going to break client software. It's going to break old implementations. Furthermore, it's probably going to cause software bugs like Heartbleed or something like that if you update a protocol that is 10 years old. It's better to deprecate the old protocol and come up with a new protocol version, which is what they did with TLS 1.2, which is a good protocol, but still has Cbc Mode in it. And that's going to be removed with TLS 1.3. The IETF process is somehow funny. It's the same process in all working groups in the IETF. People come up with a subject on the mailing list. People discuss it on the mailing list. Once there's an IETF meeting, you can go there by flying there or participating remotely. They do a vote basically on which drafts and which proposals to take and which proposals they won't take. And they do it basically by humming. So they do and the more people that hum, that easier it is for a question to be to get an answer on a certain question, like, do we take this draft? Do we take another draft? Is this draft bullshit? All these questions have been asked. Some of these people are very vocal and very political. So it's funny to listen to IETF working groups. It's really interesting, actually. And they have the best engineers there. And nowadays, they also have the best cryptographers there. So I'm really looking forward to TLS 1.3. It looks like a really good protocol. I've not seen any flaw with it.
One last question. Quick one. Any takers? No one? Okay. Well then, thank you, Aaron.